So our next speaker is Katharina Zweig, who we have to thank for an awesome review of one of our past symposia. So she talks about human navigation in complex networks, and I'm very interested to hear what you have to say, because I heard a talk by somebody, by Hannah Bast, who gave the talk about the traffic application she has with the same algorithm. So I really want to know what goes on with words here. Okay, thank you very much.
So if giving you an awesome review makes you get invited here, I will give you one every year. But it's easy to give you an awesome review because it's always an extraordinary event, and I'm very grateful to be here and to speak to you about this research I did. I did it with an Indian doctoral student. It was mainly his idea, and I added some network analysis intelligence, and I will tell you now what it's all about. So how do we navigate in real spaces? What do we know about human navigation? So all of us came here, so most of us are not from here, so you navigated this environment. And what did you do? Maybe you picked some visual landmarks, and then once you identified your landmarks, like for example the coastline of the lakes or the layout of the streets, then you put it in your memory, and this helps you to navigate in real and virtual spaces. To define a visual landmark, we can say that it is defined in physical space as having key characteristics that makes them recognizable and memorable in the environment. And I'm sure that all of you picked some visual landmarks when you were navigating here in the last few days. So the interesting thing is that humans are not very good at it. So especially in exploring complex buildings, there was a study in which nurses were asked to denote the shortest path between two rooms in the hospital. And they were working there for 2 or 3 years, and they couldn't give the shortest path between the two rooms. So what happened here? Are we a failure in exploring complex networks? And why do I speak of networks all the time? That's, of course, if you have a hammer, everything looks like a nail. I'm a complex network analysis guy. So, of course, for me, navigating in an environment is a network task, because you can connect all these places by path, and then you are asked to get from one place to the other. If you have such a network, then we know how to navigate it. For example, computers are navigating complex networks, namely the internet, every day. How do they do that? If you send them a packet, they will look up in pre-computed routing tables where to send it to next. So it's a local decision based on a globally pre-computed thing. If you have a navigation system in your car, also this has a pre-computed table and can tell you where to go next, depending on where you are at the moment. And if you're a human, the first thing I did yesterday was to pick a map, of course, from Evanston to get my way around. And again, here we have some global overview. There's some pre-computation. And with this, it's quite easy to find an optimal path. So the question is, what do you do if you don't have a global overview? Like if you have to navigate a social network. And of course, all of you know the famous small word experiment, in which people were asked to hand a letter to some person of which they only knew the name, the occupation, and the location. And the special trick was that they couldn't send it by mail. They needed to give it to an acquaintance. And that was the only way to get the letter where it needed to come to. And a friend was defined as someone you know the first name of. So, but I hope that all of us here don't have only a single friend. Most of us have many of them. So the next question is, what is the best friend to give your letter to? How do you navigate your social system? And what they found out, the few letters that reached the target, they actually made big hops in the beginning, geographically. And in the end, they were making some zigzag movements to finally hit the target. And not many of the letters actually made it. So what happened here is actually that, again, global knowledge was used something like geography and also social knowledge. People try to find someone in their acquaintances, among their acquaintances, who has a similar occupation. And the question for us was now that if we strip a network of all of these helpful environmental signs, how do people navigate a network like that without any environmental clue? And the network we came up with is actually an old children's play. The question is, how can you turn a dog into a cat without being a geneticist? Yeah, just try it. It's an old word game. You try to come from dog to cat by exchanging a letter at a time and only use correct English words. Does anyone have a solution? So I think I've heard this one. Dog, dot, cot, cat. Yeah, so this is one of the solutions. So what did you just do in your head? So you had maybe some part of this network you had, and you knew that, okay, cat can go to tat, and to cap, and to cot. And now you try to find a short way between this node here and that node here. So we call that a word network. But that is only a very small part of it. So the full thing looks like this. And nobody of you can have this full network in your head and really try to find the shortest path. It's nearly impossible. So what you see here is actually a colored version of it. It's an automatic coloring. That means I didn't do anything. So what the algorithm tries to find is words that are densely interconnected. There's a connection between two words if they differ in just one letter, because that is a step you can do in the game. So any ideas why we have 5 clusters here and what is here? Three-letter words. So any idea why there are 5 clusters here? Vowels, yeah. These are the ones that have a vowel in the middle. These are the ones with I, with U, and with O. And I would like to remind you that this is an automatic coloring. So the information is really in the network. So any ideas what's wrong with these guys? They don't have a vowel in the middle. They have it somewhere else. So it's like H, where a consonant is in the middle, or try, or ivy, icy. So these are the difficult words to get to and to get away from. So what did we do? We had some participants and we let them play this game. They got a starting word and a goal word. And for every word they were currently at, they got all the admissible neighbors. So they didn't have to have the full network in their head. They got a choice. But the problem is, it doesn't help you much. The word itself doesn't tell you whether it's nearer to the goal or not. There's not really an optimization function, but the people try to find one. So are people good at playing this game? Not particularly, actually. So we started the game with actually simple puzzles, but what happened is that this is the number of games played. This is the number of time it took in minutes. And you know, they started with 20 minutes on average. And after the 10th game, they were still having a hard time of 10 minutes finding some solution to the puzzle. So participants were quite frustrated. What they tried to do, their strategy, we asked them, they tried to move closer in every step. So we could do that with a dog-cat example. In each step, we got one letter right of the goal state. But of course, you cannot always do so. So with these examples, these are shortest path. From boy, you need to go to bay, and that doesn't look any closer to pear than boy itself. So, and these cases are difficult, if you remember the big picture, because they navigate between different clusters. One that has a vowel in the middle, and one that is somehow, oh no, this is not a good example, but car and shy is a good example. So, but then some miracle appeared. After about 28 games, they took 30 seconds per game. Whatever you gave them, they could solve it immediately. And it stayed that way. So what happened at that time point? The people started to use a landmark word. So despite the fact that the environment doesn't give you much global clues, they identified landmarks, and they started to use it. And they always used it to get there and then to get away from it to the goal word. So it's like always going into the middle of the town, no matter where you want to go, and then try to find some bus going out again. And the question is, if this is really the right analogy, are these landmark works really in the middle of something? Can we quantify that being in the middle? Yes, you can try to by using a centrality index. The most famous centrality indices try to quantify centrality in a network. Degree is just the number of nodes you are connected to. Betweenness counts more or less the number of paths that need you in the middle. And closeness centrality is just the sum of the distances to all other nodes in the system. And it turned out that this one was a good candidate. So what happened was this. We can now rank every node according to its closeness centrality. And then if this is a path, we can just assign the number according to the closeness centrality. So this is not a very central word. And in this path, it's hard to see any central word, maybe day. So this path, if you put it here, these are the words in the sequence they were used in the game. And this is their centrality. Then you see that people are really randomly walking across the network and they don't have a clue where to go to. This is one of the paths in the first 20 games. After a while, the paths looked like this. They went straight to some center and then straight out again. And this is what we then called the landmark word. But of course, none of the participants had any global overview of the network, and they couldn't have known about these ranks. So it's just what happened. So and it's exactly the time point where the people started to become really, really fast. They could solve any puzzle we gave them within half a minute. In all subsequent games, from then on, the path looks like this, and so we gave it a name called a center strategic path. But of course, so when you look at this structure, it might be that somehow the people are forced to use a central word. So maybe because the hard puzzles are always involving one from here and one from here, maybe there are only a few bridge words that you kind of have to use to get from one side to the other. To rule this out, we tried all the puzzles we gave to the participants and compared it against random walks. And we measured how often a random walk would have such a center strategic structure. And what we found is that these are the human-generated paths, and almost 80% of them, or 75% of them, have this one minimum structure. But if you do a random walk, you will not see this behavior as often. So we are quite sure that it's not dictated by the network structure itself. So if this is what people do, then the next question is, are these center strategic paths really those that are most efficient? Are they the shortest path? And no, they aren't. They're on average longer by a factor of 1.7. So you go almost double the way you would have need to go. But on the other hand, there is some efficiency to that, because if you have such a landmark word, you do not need to learn the full network. So there would be almost a million pairs of words and almost a million shortest paths between them that you would have to learn to navigate the network according to shortest path. But if you have a landmark word, then you just need to learn n paths to the words. And then you can combine by going there and going away from it. So it's only a fraction of what you need to learn if you really want to be the smartest guy navigating the network. And it doesn't cost you so much more. Yeah, the path is only double as long. So I think that there is some efficiency criterion at work here, but it's a different one. It's not about shortest path. It's about learning to navigate in this complex network very quickly. And as I said, there would be a million pairs of word of words. And the participants only played, let's say, 30 games. And after 30 games, they knew the network good enough to find a way very, very quickly. Yeah, so this is only 30 games, and then they find some way very fast. It's not much worse than the best one, and it might not be the best one. And what I think is really interesting is that in this almost environment-free environment, still people make up their own landmarks. It seems to be something that is inborn to try to single out something. So not all the participants had the same landmark words, but all of them showed the same characteristic to be somewhat in the middle of the network. We're not only doing this one, so actually this piece of research transformed my own research. I now want to go much more into that area, mixing psychology and network analysis. We are now analyzing 2 other types of games and try to find out what is the structure of the possible network of possible moves, and what is the structure of paths that are actually taken by participants. And so we look at other games, we look at other types of navigating behavior, and we try to model and find the rationale behind finding a way to a goal. So to sum up this research, we learned earlier that these nurses never learned to move the hospital efficiently. But maybe they did so because they had another efficiency criterion. So maybe their efficiency was to learn the network fast and to literally get wayfinding out of their way. Because actually it was not measured whether thinking about the really shortest path and going there would have taken longer than just taking some way that they had in mind very quickly. So this was joint research with Sudarshan Iyengar, who came up with the project, his doctoral father, and another student working on that. Thank you very much for your attention.
Yeah, there's a question first. Petter, just give me a second.
Okay, hello, I'm Petter Olmer from Sweden, and thank you, Nina, for an awesome talk. I really like this stuff. So about like spatial navigation, I know there are some people that use it a lot more than others. Taxi drivers, for example, and I know of some research where they measured the size of different parts of the brain, and it turns out that cab drivers have much larger hippocampus than other people. So I just wonder if there are some like network navigation taxi drivers, and if they have some other part of the brain bigger maybe.
So I think the interesting stuff of this research was that all participants learned to navigate the network very quickly. So they had to suffer through 3 hours of pain to understand the network, but after that learning phase, all of them managed it. So I think that was way too quickly to really change your neuronal activities. And is your question whether others could have learned it easier because they already have pre-wired capabilities?
I guess mostly if there are people like your taxi drivers when it comes to network navigation. Sorry. Okay, again, I mean, mostly if there are some like network navigation taxi drivers that use network navigation more than other people that have to do it in their profession, maybe.
Maybe I can add to this. In my former life, I was a courier driver. And there's another strategy, which is if you're standing in the part of a town where there's a city map on the street, you can go to any other location in the town by just turning 3 times. So you have to memorize 3 street names. Obviously, it's not efficient, but it takes you to the location without having to look for another street map if you don't have Google Maps. That's a long time ago. There's another question.
So I'm very interested in how students actually navigate the sticks and balls figures that we use to represent networks themselves, as opposed to the networks that they represent. And I'd be interested to know if there's any aspect of your research that involves that.
No, not currently. I've done that in the past, but not currently. And in this case, we hid the network from them because they could choose from all neighbors directly.
there's time for one more question. So.
I'm just curious what other games you're looking at. I'm thinking of things like the Rubik's Cube or those puzzles with like metal pieces linked together, and you often have to go what looks like the wrong way to get to the right way. Are you looking at any physical puzzles like that?
So we're exactly looking at this point because it seems that humans are not very good if the solution somehow involves going back. Yeah? They seem not to like it. So we devised a very simple puzzle, and all of you are very much invited to play it actually, where you have, oh, I don't know the name of it, this Springer in chess, the horse. Yeah, and you need the knight. Yes, you need sorry, you need to get it to some goal state, and we have points where it cannot go to. And so sometimes they are forced to move backwards to go faster to the goal. And we want to understand how often they will use the unintuitive solution. So maybe you shouldn't play the game after all, because I told you now what we're looking at. So, but this is one of the games we're looking at.
Let's thank Katharina Zweig again.